It is one of the 7 industrial wonders of the modern world. A wall of concrete weighing 6.6 million tons, wedged into a canyon to tame the most powerful river in the American Southwest. An icon of human ambition, and deep within the valleys and cities that it powers, 25 million people depend on it for electricity, for their lights, for their water, for their survival. When its turbines stop, and they will stop, the power grid that supports modern life in 3 states will face an immediate catastrophic failure. Not a brownout, something worse. A cascading collapse, a blackout from which there is no easy recovery. The reason is a simple number, a water level that is dropping year after year, closer and closer to a cliff. But here's the truth no one is broadcasting. The dam is facing another failure. A silent disease growing inside the concrete itself, a weakness that was poured into its foundations nearly a century ago. If this is your first time here, you're about to see why our subscribers don't miss an upload. We give you the information that sits just below the surface of the news. To make sure you're not left in the dark about the real risks to our world, hit that subscribe button right now. It is your single best defense against being unprepared. This isn't entertainment, it's an early warning. Let's begin. Picture the American Southwest before 1936, the Colorado River, a wild, untamed force of nature. In the spring, snowmelt from the Rocky Mountains would turn it into a raging torrent, flooding farms and communities. By late summer, it would shrink to a fraction of its size, leaving the same land parched and desperate for water. It was a cycle of boom and bust, of flood and drought, unpredictable, unreliable, unconquerable. Then came the dam. Hoover Dam. What you see when you look at it is more than a structure. It is a declaration, a statement that humanity could bend nature to its will. It rises 726 feet from the canyon floor. At its base, it is 660 feet thick. The amount of concrete used to build it could pave a 2-lane highway from San Francisco to New York City. The undertaking was monumental. It required rerouting the entire Colorado River through 4 massive diversion tunnels, each 56 feet in diameter, blasted through solid rock. It was a project born of the Great Depression, a symbol of defiance in an era of collapse. Thousands of men worked in blistering heat, breathing carbon monoxide in the tunnels, dangling from ropes to clear the canyon walls. It was brutal work, deadly work, but it created something that had never existed before: certainty. With the dam in place, the wild river was tamed. Upstream, the water backed up, forming the largest reservoir in the United States, Lake Mead. Downstream, the flow became predictable, controlled. For the first time, the Southwest had a reliable supply of water and power, a foundation upon which to build a new world. And we built it. Las Vegas, a small railroad town, exploded into a global entertainment capital. Los Angeles swelled into a sprawling megacity. Phoenix rose from the desert floor. Vast agricultural valleys in Southern California and Arizona, once arid, became some of the most productive farmland on Earth. But none of it would exist without the dam. None of it can survive without the dam. The lights of the Las Vegas Strip, the air conditioners in Phoenix, the pumps that deliver drinking water to San Diego. All of it is powered by water falling through concrete. The mechanism is a work of industrial genius. Simple, powerful. It all begins with the intake towers. 4 immense structures of reinforced concrete that stand in Lake Mead, just upstream from the dam itself. They are the gateways. Each tower is 395 feet high. At different elevations, they have gates that can be opened to allow water from the lake to enter. From the intake towers, the water is channeled into 4 enormous steel pipes called penstocks. Imagine a pipe so large you could drive a truck through it. That is a penstock. These pipes plunge downward through the rock and concrete of the dam, carrying the water toward the power plant at the base. The weight and pressure of the water in these pipes is immense. This is the key to everything. The entire system is a machine for converting the potential energy of stored water into kinetic energy. It converts height into motion. At the bottom of the penstocks, the water, now moving at tremendous speed, slams into the blades of massive turbines. 17 of them in total. Each one is a masterpiece of engineering, spun by the relentless force of the Colorado River. The turbines are connected by shafts to generators. As the turbines spin, so do the generators. And the generators do one thing. They make electricity, billions of kilowatt hours per year. This electricity flows into the grid. It has a complex web of high-voltage lines that feed cities and towns hundreds of miles away. It's an elegant system. It has worked almost flawlessly for nearly a century, but it has a fatal dependency. One single variable that governs everything: the water level. The height of the water in Lake Mead. This water level has a name in engineering: hydraulic head. It is the vertical distance between the surface of the lake and the turbines below. The higher the water, the greater the pressure. The greater the pressure, the more force hits the turbines. The more force, the more electricity is generated. The entire output of Hoover Dam is a direct function of that single number, the lake level. If your home has ever experienced a power outage, even for a few hours, you know the disruption it causes. Now imagine that across an entire region. What's the first thing you think would fail in your city if the power was out for 3 days? Let me know in the comments below, and that number is falling. For 2 decades, the American Southwest has been in the grip of a megadrought. This is not a normal dry spell. It is the driest 22-year period in at least 1,200 years. A fundamental shift in the climate. The source of the Colorado River is the snowpack in the Rocky Mountains. Year after year, that snowpack has dwindled. Less snow means less meltwater in the spring. Less meltwater means less flow into the Colorado River. And less flow means Lake Mead is being emptied faster than it is being refilled. You can see the evidence with your own eyes. It's called the bathtub ring, a stark white band of mineral deposits staining the canyon walls around the lake. That white line marks where the water level used to be. Every foot of that stain represents billions of gallons of water that are no longer there. In the year 2000, Lake Mead was nearly full, at an elevation of about 1,220 feet above sea level. Today it has fallen by more than 170 feet. It is a fuel gauge, and it is pointing toward empty. The problem isn't just the drought, it's a mistake made 100 years ago. The Colorado River Compact of 1922. This was the agreement that divided the river's water among 7 states, but the deal was negotiated during one of the wettest periods in the region's history. The men who wrote the compact overestimated how much water the river could provide. They promised more water than nature could deliver year after year. For decades, it didn't matter because the reservoir was full. It acted as a buffer, but now the buffer is gone. The bank account is overdrawn. We are taking more water out than the river provides. A simple, brutal arithmetic. The consequences of this decline are not theoretical. They are governed by the physics of the dam itself. There are critical elevations, numbers that represent thresholds, tipping points. The first and most immediate threshold is 1,050 feet. 1,050 feet. Below this level, the turbines at Hoover Dam can no longer operate safely. The hydraulic head, the pressure from the water, becomes too low to spin the turbines at their designated speed without causing catastrophic damage. A phenomenon called cavitation. Imagine running a boat propeller partially out of the water. It churns air and water together, creating violent vibrations and vapor bubbles. When those bubbles collapse, they do so with incredible force, blasting tiny pits into the metal. Now, scale that up to a 500-ton hydroelectric turbine. As the water pressure drops, air can get sucked into the system. Vapor bubbles form and collapse against the steel turbine blades. Each collapse is like a tiny shockwave. Microscopic explosions that over time eat away at the metal. It's like a form of high-speed erosion. It tears the turbines apart from the inside. The operators know this. The Bureau of Reclamation, the federal agency that runs the dam, knows this. They cannot run the turbines in a state of cavitation. It would destroy them. So as Lake Mead approaches 1,050 feet, they will have no choice. They will begin shutting the generators down, not all at once, one by one, a strategic retreat in the face of a losing battle. First, the power output will become erratic. Then whole generator units will go offline. Hoover Dam's capacity will be systematically dismantled. Losing this power is not like losing any other power plant. Hoover is not just a source of baseline electricity. It is a critical stabilizer for the entire Western electrical grid. It's known as a peaker plant. When demand for electricity spikes, like on a hot summer afternoon when millions of air conditioners turn on, the grid becomes strained. To prevent a blackout, operators need to bring more power online instantly. Most power plants, coal, natural gas, nuclear, can't do that. They take hours or even days to ramp up. But a hydroelectric plant can. At Hoover, an operator can open a valve, and within seconds, a generator can go from idle to full power. This ability to provide power on demand is what keeps the grid from collapsing during periods of extreme stress. It is the shock absorber. It is the safety valve. If you know anyone living in Arizona, California, or Nevada, this next part is something they absolutely need to be aware of. Hit the like button to help this video reach them, and please share it with your family and friends. This isn't just a news story, it's a matter of regional security and personal preparedness. When Hoover Dam loses its ability to function as a peaker plant, the entire grid becomes brittle, fragile, vulnerable to the slightest disruption. A heat wave, a wildfire taking out a transmission line, another power plant going offline unexpectedly. Any of these could trigger a failure that doesn't just stay local, it cascades. Think back to the Great Northeast Blackout of 2003. A single transmission line in Ohio, sagging into a tree, set off a chain reaction. The line tripped, rerouting its power to other lines. Those lines became overloaded and tripped. Within minutes, the failure cascaded across 8 US states and parts of Canada. 55 million people lost power. The cause was a single point of failure in a system that had lost its redundancy. Losing Hoover Dam creates a far greater vulnerability. It removes one of the most important safety mechanisms from the Western grid. The result wouldn't be a temporary outage. It could be a sustained, large-scale blackout affecting major metropolitan areas like Los Angeles, Phoenix, and Las Vegas. A world without power. No lights, no refrigeration, no air conditioning in 110-degree heat. No traffic signals. No gas pumps, no ATMs, no water service, because the pumps that pressurize the water mains require electricity. Within hours, a modern city would grind to a halt. This is what happens when Lake Mead drops below 1,050 feet. It's not a distant possibility, it's a calculated engineering certainty. The lake has hovered dangerously close to this number in recent years. Only emergency water releases from upstream reservoirs and a few wet winters have kept it just above the line. But the long-term trend is undeniable, downward. We're about to expose a danger far more permanent than a power shutdown. The official reports mention it in technical appendices, but they don't spell out the terrifying implications. If you trust that we deliver insights you won't get from mainstream sources, you must be subscribed. This isn't just about watching a video, it's about arming yourself with knowledge. Hit subscribe now because what comes next changes the entire problem. The water level is only the first crisis. The second is older, more insidious. A problem that was literally mixed into the dam's concrete nearly a century ago. It is a chemical reaction, a slow, relentless process called alkali-silica reaction. A SR concrete seems like inert, permanent rock. It is not. It is a complex, active chemical brew. It's made of cement, water, and aggregates, the sand and gravel that provide bulk. In the 1930s, when Hoover Dam was built, the science of concrete was still developing. Engineers did not fully understand that certain types of aggregate, those rich in silica, could react with the alkaline chemicals present in the cement paste over decades. This reaction creates a gel, a hygroscopic gel. That means it absorbs water, and as it absorbs water, it expands. The expansion force is immense. It happens from within the concrete itself. It generates a network of microscopic cracks. The concrete slowly swells, losing its strength, its integrity. It is a cancer that grows in the heart of the structure. Hoover Dam was built using aggregates dredged from the Colorado River. Aggregates that, it turns out, were reactive. For decades, engineers have known that Hoover Dam is suffering from ASR. They monitor it constantly. They measure the growth, the swelling of the concrete, in millimeters per year. For a long time, it was considered a manageable problem, a kind of chronic illness that could be monitored but wouldn't be fatal. But the current water crisis changes the equation entirely. The massive, unprecedented fluctuations in the level of Lake Mead are subjecting the dam to stresses it was never designed to endure. Think about it. For decades, the lakeside face of the dam was submerged, kept at a relatively constant temperature by the massive body of water. Now, hundreds of feet of that concrete face are exposed to the air, to the brutal desert sun. It heats up during the day. It cools rapidly at night. This thermal cycling, this expansion and contraction exacerbates the damage caused by ASR. The water level itself dropping and rising creates cyclical loading and unloading of pressure on the structure. The wetting and drying of the concrete as the lake level fluctuates can accelerate the chemical reaction. The illness is becoming more aggressive. This isn't an external threat like an earthquake, it's an autoimmune disease. The dam is, in a sense, destroying itself from within. The danger is not that the main arch of the dam will suddenly collapse. The structure is too massive for that. The real danger is localized failure. Failure in the most critical components. The intake towers, the penstocks, the spillways. These are the parts of the dam that are more slender, more complex, and more vulnerable to the swelling and cracking from ASR. Imagine a crack forming in one of the 4 intake towers, a crack that compromises its structural integrity during a period of low water and high thermal stress. If a piece of that tower were to fail, it could block the intake gates. It could prevent water from entering the penstocks, or worse, an uncontrolled failure could lead to a breach. A similar failure in the concrete surrounding the massive steel penstocks could be catastrophic. These pipes are under immense pressure. The geology and engineering are a unified system. If the concrete that encases them fails, the forces are unimaginable. You don't just lose power, you could lose the ability to control the flow of the river entirely. This isn't a scenario where the lights go out. This is a scenario where the most important piece of water infrastructure in the American West breaks in a way that might not be fixable. You cannot easily repair a structural failure hundreds of feet underwater or deep inside a million-ton block of reactive concrete. The problem shifts from no power to no water, a permanent failure, and that brings us to the second critical number, the final cliff, 895 feet. And this is the elevation of Deadpool. Let's be clear about what this means. Deadpool does not mean the lake is empty. There would still be a vast amount of water in Lake Mead, millions of acre-feet of it, but at 895 feet, the water level would be below the lowest intake gates on the dam. The dam would be blind and mute. It could no longer release water downstream. By the laws of gravity, the Colorado River, as it flows past Hoover Dam, would cease to exist. It would become a dry riverbed. The consequences of this are almost too large to comprehend. The water supply for all of southern Arizona and California that comes from the Colorado would be gone. The water that irrigates millions of acres of farmland would vanish. The treaty obligations to deliver water to Mexico would be impossible to meet, and most immediately, it would mean the death of Las Vegas. The city's water intakes are not part of the dam. They are separate pipes placed in Lake Mead. But if the lake drops to Deadpool, those intakes will eventually be sucking air. The city of Las Vegas would lose its primary source of water. Not temporarily, permanently. So why isn't this the lead story on the news every single night? Why are people still building homes in Phoenix? Why does life in these cities continue as if this existential threat doesn't exist? The reason is a quirk of human psychology, a cognitive bias called normalcy bias. The sun has risen every day of our lives, so we assume it will rise tomorrow. Hoover Dam has provided power and water for our entire lives, and our parents' lives before that. So we assume it always will. The threat is real. The numbers are clear. Like the trend is undeniable. But it's a slow-moving crisis, a creeping problem. It unfolds over years and decades, not seconds and minutes. Human brains are wired to react to immediate threats. A tiger in the grass, a car swerving into our lane. We are not good at processing slow, abstract existential risks. The danger feels distant. It's not as real as the mortgage payment due next week. It's not as urgent as the traffic on the way to work. And so, we collectively engage in a form of denial. We trust that someone, somewhere will figure it out, that technology will save us, that it will rain. This bias is reinforced by the sheer scale of the solution. The problem is simple. There is not enough water. The solution would be to create more water or use dramatically less. Both are almost impossibly difficult. Can we create more water? Proposals have included towing icebergs from the Arctic. That's science fiction. A more realistic idea is large-scale desalination of ocean water, but building enough desalination plants to offset the Colorado's deficit would cost hundreds of billions of dollars, and they would consume an astronomical amount of energy. To solve a crisis caused by a lack of hydroelectric power, we would need to build a whole new generation of power plants just to run the desalination plants. The math doesn't work. The energy cost is self-defeating. So what about using less water? That means making choices. It means telling farmers in the Imperial Valley that the water they have used to grow crops for a century is no longer available. It means telling the city of Phoenix that it cannot approve new housing developments. It means telling 25 million people that the lifestyle they have known is over. These are politically impossible conversations. No politician wants to be the one to deliver that message. And so, the path of least resistance is to hope, to manage the crisis year by year, to make small cuts, to pray for snow, to rely on normalcy bias. The dam has always been there. It will be there tomorrow. Let's make this personal. Picture a family living in a suburb of Las Vegas. It's July. The temperature outside is 117 degrees. For weeks, the news has been reporting on the strain on the power grid. Lake Mead has finally dipped below the 1,050-foot mark. Hoover Dam is operating at a fraction of its capacity. A wildfire in California takes out a major transmission line. The grid, now stripped of its primary shock absorber. I can't handle the sudden imbalance. The fail-safes kick in. The system begins to shut itself down to prevent a catastrophic overload. The lights in the family's home flicker once, twice, then go out. The air conditioner falls silent. It's not just their house, it's the whole neighborhood, the whole city. Their cell phones still work for now, but the local cell tower is on backup power, which will only last a few hours. They turn on a battery-powered radio. The reports are confused. A cascading failure. Los Angeles is dark. Phoenix is dark. No one knows when the power will come back on. Days, maybe weeks. The refrigerator is full of food that will spoil. The temperature inside the house begins to rise. They have a few cases of bottled water, but when that runs out, what then? The city's water pumps are silent. No, there is no pressure in the taps. Outside, the world has stopped. Traffic lights are out. Gas stations can't pump fuel. Every system that underpins modern life has vanished because a single number, a water level hundreds of miles away, crossed an invisible line. This isn't a movie plot. This is the direct, predictable consequence of infrastructure failure on a regional scale. It is the reality of what happens when a civilization builds a magnificent machine in the desert and then forgets to check the fuel gauge. The story of Hoover Dam is a parable for our time. It's a story about ambition, ingenuity, and the ultimate power of nature. We built a monument to our own power, and for a century, that monument delivered on its promise. It allowed us to build cities in the sand. It gave us light and life in one of the most inhospitable places on the continent, but we became complacent. We took the machine for granted. We assumed the river it tamed was infinite. We assumed the concrete it was made from was immortal. Both assumptions were wrong. The river is finite, the concrete is mortal. The systems we build, no matter how grand, are subject to the laws of physics and chemistry. The drought is a physical reality. The ASR is a chemical reality. These forces do not negotiate. They do not care about our economy. They do not care about our political squabbles. They simply act. And their actions are now pushing Hoover Dam toward a state of failure. The irony is heartbreaking. A structure designed to provide certainty is now the source of the greatest uncertainty in the American Southwest. It is a ticking clock. But we don't know exactly when it will strike zero. These deep dives into the fragility of our world are why this channel exists. To understand the systems we depend on is the first step toward resilience. If you believe in this mission, make sure you are subscribed. It's the most powerful way to support this work and ensure these stories are told. What we are witnessing is a collision of timelines. The geological timeline of climate change is crashing into the human timeline of our society. The dam was built to last for centuries, but it was built with assumptions from a world that no longer exists. A world with more water, a world with a more stable climate. The engineers who designed it were brilliant, but they could not predict the pressures of the 21st century. Now, we are left with their legacy, a magnificent, dying machine. A monument that could become a tombstone. When its turbines finally fall silent, it will not just be the end of a power plant. It will be the end of an era, the end of the belief that we could conquer the desert. The desert, it turns out, is patient, and it is winning. The silent, empty powerhouse at the bottom of the canyon will be a testament to a hard lesson. A lesson that for a century we chose to ignore. The lesson that in the end, nature always sets the terms.